Hello everyone, welcome to ETEC221 lectures again. Today's lecture is lecture 6, Oscillators Part 2. The LC oscillators. So far we have analyzed feedback oscillators which utilize RC components, but they are suitable only for frequencies up to 1 MHz. The LC feedback elements are normally used in oscillators that require higher frequencies of oscillations. In addition, discrete active devices such as BJTs and FETs are used instead of op-amps due to their frequency limitations. That means that individual active devices can operate at much higher frequencies. The general configuration of LC feedback oscillator looks like this. We have, of course, amplifier, and between the amplifier's output and input we have a feedback network, which is consisted of three reactances, X1, X2, and X3, and they form a shape of delta or P configurations. Now, depending on the type of those reactances, we can distinguish several different oscillators. For instance, if X1 is a capacitor, X2 capacitor, and X3 inductor, we call this Colpitts oscillator. Hartley oscillator will have X1 as inductance, X2 as inductance as well, and X3 will be a capacitance. If we don't have at all X3, but X1 and X2 are LC components in both cases, we call that tune input, tune output amplifier. All LC feedback oscillators use resonant circuits in the feedback path. A Colpitts oscillator utilizes a resonant circuit consisted of one inductor and two capacitors in series, as shown in enclosed schematic. The resonant frequency of this tank circuit is the frequency of oscillation. The function of an amplifier A is only to replenish energy losses due to power dissipation of resistive components present in the circuit, either as resistive loads or as a parasitic resistances of reactive components L and C. This amplifier is not an op-amp, but rather discrete active device like high-frequency BJT or JFET. Usually C2 is the larger capacitor because it develops smaller voltage, which is exactly a feedback voltage VF brought back to the input of the amplifier. Recall that in series capacitors, the same charge is deposited on both, and it is proportional to the product C and V. C, capacitance, times voltage across the capacitor. Since capacitance C2 is much larger than C1, it will develop much lower feedback voltage. The resonant frequency of this circuit can be found by expression Fr equals 1 over 2 pi square root of L C total, where C total is a series combination of two resistors and it's given as C1 times C2 over C1 plus C2. This expression is valid if the Q factor of the tank circuit is higher than 1. Assuming that the resonance circuit is not loaded heavily with external impedances, that means we will assume ideal conditions. The resonance circuit alone operates as follows. Inductor and capacitors exchange energy between magnetic and electrostatic field. Say that at one instant all energy is stored in magnetic field. The inductor's induced voltage becomes a source in tank circuit producing the same current through both capacitors in series but the different voltages across them depending on actual capacitance C1 and C2. So once again, let's take a look into this schematic. Induced voltage VL across the inductor now is the source of AC signal for this tank circuit, providing a current through both capacitors, which are in series. The current flows from the higher potential through the closed loop to the lowest potential. So depending on the capacitance C1 and C2, there will be different voltages across capacitors. As you can see, our feedback voltage VF is taken from the capacitor C2 and it matches polarity of the capacitor voltage VC2. However, the output voltage is the voltage across capacitor C1, but the voltage across this capacitor has opposite polarity. So when we define feedback factor beta as a V off over V out, the Vf gets a value of the voltage across C2, but the Vo gets a value of negative Vc1. If we express voltage as a product of the reactance and current that flows through the capacitor, which in both capacitors will be the same, you will get this expression, substituting xc1 with 1 over omega c, and cancelling out omega c and omega c I and I, you will get simple expression that the feedback factor is a ratio of two capacitors, C1 over C2. Since C1 is much lower than C2, we already mentioned that this ratio will give us very small number. The Hartley oscillator is similar to the Colpitts oscillator, except the resonance circuit consists of two series inductors, or a single tapped inductor, and a parallel capacitor. The feedback voltage is developed across inductor L2, which is much lower than L1. Recall that the same current flowing in series inductors will induce voltages proportional to inductance values. So V1 or 2 is equal L1 or 2 times current flowing through those inductors. The frequency of oscillation for the quality factor higher than 10 is given with this expression, 1 over 2 pi square root of LT times C, where LT designates total inductance of the tank circuit, which in the case of Hartley oscillator will be L1 plus L2. If you look at the schematic, you should also notice two additional capacitors, but they do not define the frequency of oscillation. They have usually much higher value than capacitance C, and the primary function is to block the DC current from the output through the short consisted of L1 due to a very small ohmic resistance. The same situation is at the input, where this capacitor will block DC current. One advantage of Hartley oscillator is that it can be tuned by using a variable capacitor in the resonance circuit. Now let's summarize the basic LC feedback oscillator. Colpitts oscillator will have one inductor and two capacitors in a feedback circuit. Amplifier is doing shift of 180 degrees and then a feedback network additional, making net phase shift of 360 or 0. Frequency of oscillation is given as 1 over 2 pi square root of LC total, and C total represents a series combination of C1 and C2. On the other hand, we have a Hartley oscillator, and delta configuration of reactive components looks like L1 and L2 in series and one capacitance. So it has one capacitance and two inductors in series. Again, amplifier is providing 180 degrees shift, and of course feedback network is then required to do additional 180 degrees. Frequency of oscillation is given as 1 over 2 pi square root of total inductance, which is made of two series inductances L1 and L2 times capacitance C. One interesting modification of Colpitz's oscillator is a so-called clap oscillator, where inductor in feedback network has a series capacitor with a very small capacitance. Now, if you look at the original Colpitz's oscillator, you will notice that there is no load attached to it. Typically, load has a certain parasitic capacitance, which is then added to the C2 in parallel, which increases overall capacitance and therefore changes the frequency of oscillation. The similar situation is with the capacitor C1, where parasitic capacitance of the active device will be added in parallel, increasing capacitance and thus changing the frequency of oscillation. In most cases, this is the situation which we are facing in our lab experiments, where parasitic capacitance are actually capacitance between breadboard rows, which has a certain capacitance associated with the mechanical design of the breadboard rows. Adding this small capacitor Cx, now we will have three capacitors in series, thus making total equivalent capacitance equal 1 over reciprocal value of C1, C2, and Cx. If Cx is much lower than C1 and C2, total equivalent capacitance is predominantly defined with this capacitance and not with C1 and C2, or whatever parasitic capacitance might be in parallel with those two. So by adding this capacitance, we are actually eliminating possible loading effect on C1 and C2. We will say a couple of words about the crystal oscillators. The output frequency of oscillator circuits is not as stable as required by majority applications. It depends on component tolerances, ambient temperature, or change with component aging or losing their nominal values. Oscillator frequency stability can be dramatically improved by the use of piezo or piezoelectric crystals like Rochelle salt, quartz, or tourmaline. Quartz is a crystalline substance found in nature that exhibits piezoelectric effect property. When exposed to mechanical vibrations, a voltage develops across the crystal at the frequency of mechanical vibrations. Conversely, when an AC voltage is applied, the crystal vibrates at the same frequency of the applied voltage. The greatest vibration occur at the natural resonant frequency of the crystal, which is mainly determined by its physical dimensions. Because the crystal resonant frequency is extremely stable, quartz is used to stabilize the frequency of oscillations. The crystal is usually mounted inside the vacuum-sealed glass envelope or hermetically sealed metal can with two silver or gold electrodes plated on the opposite sides of electrical connections. Now you see here at the picture A, typical package of the crystal in a metal can. B indicates the basic construction without the case. This would be electrical symbol, and electrical equivalent of this crystal is given with this diagram. It's consisted of a series inductor, series capacitance, and series resistance, and the parallel combination of parasitic capacitance between the electrodes of the quartz wafer. We know now this piezoelectric effect actually is what we are utilizing in all crystals. When you compare Rochelle salt, quartz, and tourmaline with respect to the piezoelectric effect, it's interesting to say that Rochelle salt has the highest piezoelectric effect. That means that the vibrations have the highest amplitude for the same voltage, however it's very brittle. Tourmaline, on the other hand, is very robust and doesn't break, however it has a very low piezoelectric effect. So quartz will be some optimum selection with respect how much vibrations we can get for a given voltage compared to the mechanical characteristics of the crystal itself. The quartz can operate in either series or parallel resonance. In series resonance, crystal inductivity Ls resonates with Cs, series capacitance, exhibiting minimal impedance equal to the equivalent crystal resonant resistance Rs. However, approximately 1 kHz above that, in parallel resonance, when the impedance becomes extremely high, parasitic capacitance Cm resonates with Ls. The parallel resonance frequency is at least 1 kHz higher than the series resonance frequency. The crystal exhibits a very high Q factor from around 2000 to approximately 100,000, which is the measure of quality of resonance, or how good is the circuit in sustaining the oscillations without losing the energy on resistive components. The smaller the quartz, the higher its natural resonance frequency. Due to the technological limitation in process of cutting the crystal slab, the oscillating frequency is limited to around 10 to 20 MHz. Now here are a couple of examples how we can utilize quartz crystal in stabilizing the frequency of oscillation. In the first case, you are looking at the phase shift oscillator. We are utilizing crystal as a feedback network between the output and the input. In this case, we would like to see the maximum voltage from the output to the input to sustain oscillation, and obviously in this case the crystal will be set up to operate in series resonance. Then it will have a minimum impedance which is equal, as we said, to series resistance. On the right hand side you have a Colpitts oscillator where inductor is substituted by a crystal. Obviously we are working here in parallel resonance, providing extremely high impedance at the frequency of oscillation. Relaxation oscillators using integrator. Relaxation oscillators are characterized by having RC timing circuit and a switching device that periodically changes state, thus providing charging and discharging of the capacitor. The triangular wave oscillator is an example. For this circuit, the device that changes state is a comparator with hysteresis, Schmidt trigger. The RC timing device is an integrator. The comparator output can be used as a square wave output. So if you look at the schematic and you look at the output of the comparator, if this output is high, positive, V out of the integrator decreases until voltage at the non-inverting terminal of U1 drops below zero. So when this input here drops below reference voltage of zero, then the comparator switches to negative Vmax, and the integrator starts ramping up, so the voltage Vout increases. Now the voltage at the non-inverting terminal goes up until it exceeds 0 volts. Then the comparator switches back to Vmax. The frequency of oscillation is given by expression 1 over 2 for R1, C, that's the time constant of the integrator, times ratio R2 over R3. The trigger points define the triangle's peak-to-peak value and the frequency as well. So upper threshold point will be Vmax times R3 over R2, and low threshold point will have the symmetrical negative value with minimum R3 over R2. To provide the best possible operation, normally triangle wave generator uses fast comparators for this switching to avoid slew rate problems. Let's look into more detailed operation of the integrator RC relaxation oscillator, and at the same time looking at the diagram of the waveform at the output of the integrator and in the output of the comparator. Let's say when the comparator output is high, like in this case 10 volts, the input of the integrator will see a positive constant voltage, Vmax, and it will start ramping down. Ramping down will lower the voltage at the output, and when this voltage drops to such a value that the non-inverting input of the U1 gets a value which is slightly lower than 0, the output of the comparator will change the level from positive 10 volts to negative saturation voltage, negative 10 volts. That would be the lower threshold point. As you can see, it's given as a negative Vmax R3 over R2. Vmax designates the lowest possible voltage at the output, which corresponds to a negative power supply voltage, or close to that value. As we said, having a negative voltage at the input of the integrator starts ramping up now. It will keep on ramping up until it reaches the point where non-inverting input of the U1 gets a value that is higher than 0. And that would be the upper threshold point, which is positive Vmax R3 over R2. Again, positive Vmax, it will be close to positive VCC power supply line. At this point, comparator is changing output from negative Vmax to positive Vmax again. And the integrator, having a positive DC voltage at the input now, will start again ramping down. Keep on ramping down all the way until the voltage at the output gets such a value that non-inverting input of U1 has a value of lower than 0. Keep in mind, voltage at the output of the comparator is not the same as the voltage to the non-inverting due to this voltage divider. Now, if we want to find upper threshold point and lower threshold points, we will use superposition theorem to determine voltage at the non-inverting terminal of the comparator. This voltage is consisted of two parts. One caused by voltage Vn here, that's the output of the comparator, and the other one due to output voltage from the integrator. Now the first one is given with voltage divider R3, R2 plus R3 times total input voltage Vn, and the second one is given with voltage divider, which is R2 over R2 plus R3 times total applied voltage Vout. So this voltage at the non-inverting terminal will have those two parts. We use superposition to find the total. Now when this voltage drops slightly below zero, then Vn switches to negative Vmax. And the output, in this case voltage, will reach lower threshold point, which is negative R3 over R2 times Vmax. That's the lower threshold point. However, when this voltage goes slightly above zero, then output of the comparator switches to positive Vmax, and output voltage reaches the upper threshold point, which is positive R3 over R2 times Vmax. Here is one example how to do calculation of the frequency of oscillation for the integrator type RC relaxation oscillator. And this is a very simple, straightforward example. The values of all values of components in the circuit are given, and we will utilize expressions of frequency of oscillation, plug in the values for R1, R2, R3, and C, and get the value of frequency oscillation. In this case, it will be 671 Hertz. Relaxation oscillators with programmable unijunction transistor. This type of oscillators utilize very specific property of programmable unijunction transistor or PUT. PUT is a four-layer device with three terminals, as can be seen from this internal block diagram: anode, gate, and cathode. So this will be anode on a symbol, gate, and cathode, just like thyristor had. From that perspective, PUT looks more like a diode rather than a bipolar transistor. It's just that it has a third-terminal gate which can be used to define the conduction point of the diode. Recall that for regular rectifying diode, as soon as anode is 0.7 higher than cathode, the diode will be on. Not in the case of PUT, where, of course, the firing point depends on the gate voltage here. What is interesting about this device is that the peak anode voltage, V peak, that's one of specification of this device, can be programmed externally using resistors, for instance, by defining the voltage at the gate. Since potential Vp can never be higher than potential at the gate for more than 0.7, we can program the point where PUT will trigger on. When anode voltage reaches this value, the PUT fires, reducing drastically resistance between anode and cathode, making it practically short. This property is widely used in relaxation oscillators because it provides control of charging and discharging of a capacitor, as can be seen from next application. One application of a voltage-controlled oscillator, or VCO, which generates a sawtooth waveform, is shown in figure below. If you remove PUT from this circuit, it is easy to identify an integrator, which, due to negative DC input voltage, will always ramp up at the output. This voltage, Vout, is actually potential of the anode, and as long as this potential is lower than potential at the gate, Vg, the PUT is off and the capacitor starts charging. This voltage Vout is actually potential at the anode, and as long as this voltage is lower than adjusted potential at the gate, Vg, the PUT has high resistance and makes no difference in the circuit. It's like an open circuit. However, when this potential, Vout, at the anode, Va, is higher than Vg plus 0.7, the PUT fires or turns on, reduces resistance between anode and cathode practically to zero, and then capacitor discharges rapidly. This would be the negative going slope of the sawtooth. So when it discharges, the voltage that reaches certain value, potential at the output Vg plus 0.7, drops to zero very quickly. When C discharges, Vout drops below firing point, and PUT goes to non-conducting state, and the new positive going ramp begins. So it always ramps up due to constant negative voltage at the input, but once it reaches value Vg plus 0.7, which can be adjusted externally, then quickly drops to zero and then starts ramping again. In this circuit, the device that changes the state is PUT, and the RC timing circuit is an integrator. The frequency can be found using this expression, and as you can see, it's a function of the constant negative input voltage Vin, time constant of the integrator, and depends on the firing point. Vf is the standard 0.7 voltage drop across the forward bias junction. Relaxation oscillator with Schmitt triggers. Another relaxation oscillator that uses a Schmidt trigger is the basic square wave oscillator. So as you can see, this oscillator can give us only square waves at the output. The trigger points are set by resistors R2 and R3. The capacitor charges and discharges between these two levels. So upper threshold point will be R3 over R2 plus R3 times positive maximum value, which is close to VCC. And lower threshold point will be symmetrical negative point, again given with voltage divider, R3 over R2 plus R3, multiplied with the negative maximum voltage at the output close to negative VCC. The period, which is a reciprocal value of the frequency, is given with the time constant R1 times C and depends on the ratio R3 and R2. Simply how this oscillator works: if we have, let's say, positive voltage at the output equal to Vmax, the feedback voltage, positive feedback voltage, which defines upper threshold point, will be given with the voltage divider, R3 over R2 plus R3 times total applied voltage, which is positive Vmax. That will be the voltage Vf, reference voltage Vf at the non-inverting point. Since we have a positive maximum output voltage, there will be charging current flowing through R1 through capacitor to ground, and voltage Vc will rise exponentially. When this voltage exceeds voltage Vf, which is equal to upper threshold point, then the output will switch from positive Vmax to negative Vmax. And in this case, our Vf becomes a negative or lower threshold point given with this ratio. Now what is happening, because we have a lower potential, negative Vmax at the output, the capacitor will start discharging through resistor R1 towards the negative voltage at the output. We will have discharging cycle. Now this voltage Vc will start dropping until it drops below lower threshold point as given here. At this moment, differential voltage will become positive and the output will from a negative Vmax switch now to positive Vmax, and we will start new cycle. The more sophisticated and more versatile type of RC relaxation oscillators come in the form of an integrated circuit 555 timer. This timer has several modes of operation, but we will focus on a stable multi-vibrator option. For this option, there are only few external components required to provide a reliable and stable oscillation. However, the output will always be only a square waveform. If you look at the block diagram of this circuit, there are two comparators, U1 and U2, having two different reference voltages as set by voltage divider consisted of three identical resistors R. This one, and that one. Usually the typical value of those resistors are around 5 kiloohms. Now, the high reference voltage is defined with the voltage divider R plus R over 3R times VCC, making 2/3 of VCC. And low reference voltage, Vref low, is defined with voltage divider R over 3R times VCC, which makes 1/3 of VCC. Instantaneous voltage across the capacitor, call it VC, is brought to both comparators, so we are comparing this voltage with the reference voltages high and low. If voltage VC is higher than Vref high, then the U2 sets output high and resets a flip-flop. However, if this voltage drops below value of Vref low, then the bottom comparator U1 goes higher and sets a flip-flop. So you can say that those comparators will set or reset a flip-flop depending on the instantaneous value of the capacitor. When this flip-flop is set, then the output Q is high, but Q inverted is low. And this low keeps the transistor in non-conducting state because there is no sufficient voltage to provide forward biasing. Therefore, transistor is in cutoff and collector current is 0. So it's practically disconnected from the charging path. In this case, capacitor will start charging through a series combination of resistors RA and RB, so the voltage will rise exponentially. When this voltage exceeds slightly Vref high, the output of U2 goes high and resets flip-flop. Resetting flip-flop will bring inverting output Q high. Now there is sufficient voltage to forward bias transistor Q into saturation, and the voltage drop between collector and emitter drops to 0, practically means that this terminal 7, which is also called discharge terminal, will be grounded. The charging stops at that moment and discharging of the capacitor through resistor RB commences. This discharging condition will last until voltage across the capacitor drops below low reference voltage. Then U1 will go high and set the flip-flop. Setting of the flip-flop will bring output Q inverted low again, and transistor will switch off. When it switches off, the new charging cycle starts again. From this explanation of operation of 555 timer, we can see that the voltage across the capacitor will always oscillate between minimum value, which is 1/3 of the VCC, and maximum value, that is 2/3 of VCC. When it reaches maximum value, 2/3 of the VCC, the top comparator will reset flip-flop, and we will start discharging because the transistor will turn on, we will start discharging the capacitor. Discharging will last until the voltage drops slightly below 1/3 of the VCC. What is happening then is that U1 will set the output high and set the flip-flop, which will again switch off transistor, and the new charging cycle will start. If you look at the shape of the signal at the flip-flop output Q inverted, you will recognize that it is a square wave. After buffering and inverting, you will have the same waveform at the output terminal 3, it's just that it will be opposite in polarity. During the charging, you will notice that our time constant is Ra plus Rb times C. However, during the discharging cycle, time constant is defined with Rb times C only. So there is a difference between charging and discharging time constant, making different duty cycles, shown here. Now the frequency of oscillation is given with expression 1.44 over Ra plus 2Rb times C. 1.44 is the reciprocal value of ln of 2, for your reference. So when you're looking at the duty cycle, you will see that it's impossible practically to make a duty cycle less than 50%. Even 50%, you have to implement different techniques demonstrated in lab exercise. And this will conclude Lecture 6, Oscillators Part 2. Thank you.